Okay, I think we're ready for this. Uh, uh, well, right now because I have some time off, and actually because right now we had to work at home because of the coronavirus and everything happening around. Some people have asked me, "Do you want to do an introduction about molecular dynamics?" And I say yes. I mean, it's gonna be fun and it's also one of my expertise. Well, not exactly one of my expertise. I mean, if you have seen my other videos about education, probably you are gonna see that many are related to what is called special ed, special education. So that's also one of the branches I have some knowledge. But my background is in physics. Okay. Then later on, I moved into what is called education. Yes, and I have been working in many branches of education, like testing coordinator, special education, science, math, Tiger One, etc., etc., and also in education leadership. But regardless of that, I still have some my real background in physics, and actually, what I'm expertise at is in computer modeling of materials under phase changes under pressure, temperature, etc., and how they behave. So we can see that based on molecular dynamics, that's pretty much in the atomic level, or we can also go into the continuum by using partial differential equations. Okay, so there are two ways to see how we can predict the behavior of materials. But anyways, so I'm gonna give a presentation about how we do molecular dynamics, and it is a basic introduction. I'm gonna go into heavy concepts. I'm gonna try to do the lecture a little bit easy for students who actually are in high school. Yes, so even the students who are in high school are gonna follow me when I teach this lesson. So what we're gonna cover, and I'm gonna put it right here. So if we continue into the next slide, what we're gonna cover? Well, uh, I'm gonna have to explain first what is molecular dynamics. So that's one of the things. So the first we had to understand was molecular dynamics, and then why we care, why we want to learn molecular dynamics, and what application we can find in real life. Okay. Then later on we can go into how to do molecular dynamics. Okay. And if I go into the topic, probably I'm gonna go into some computer software that is already for doing that, like amber lamps, etc., and I'm probably giving introduction on how to run some, how to compile some of these programs, and then I'm gonna continue to well-known problems can be solved using molecular dynamics. There are some problems that can be really be the molecular dynamics is really useful. Okay. And we can, for example, predict phase changes under temperature or how materials compress under different conditions, etc. Then I'm gonna go into interatomic potentials, and finally, right here, if you have any feedback or you have any comments or you want me to explain something that was not really clear, please give you some comments, and I will try to reply as soon as possible into that. So let's go into the first topic, what's molecular dynamics. So molecular dynamics is pretty much straightforward. And well, you have to have some background physics to understand this. But number one, Newtonian mechanics predict the behavior of a system as time progresses. Probably, if you remember from high school, I think you remember Newtonian mechanics. Okay, you can predict how it's gonna be the position of an object as a function of the time. Okay, and pretty much when you are referring to Newtonian mechanics, we have the initial conditions of a system, yes, that you can predict for a later on time. And this is based that Newtonian mechanics is deterministic. Okay, so when you have your initial conditions and you let the system run, then you can try what happen straightforward. How are we gonna find, or how are we gonna find the solutions to the Newtonian equation? So how are we gonna find that? How are we gonna compute that using different methods? Well, remember you had to use your numerical integrator. So pretty much when you are referring, and probably that's more into when you're going to college, when you're going to Newtonian mechanics, and actually the equation is the force equal the mass times acceleration. Uh, Probably you're gonna notice that that's a second order differential equation. Okay, so there are different techniques or different numerical methods that you can use to find the solution to differential equations. The one I'm going to explain right here is the basic storm Verlet. And I'm going to read right now. For a second order differential equation of the type, and probably some people are going to understand this was, we have the x and you have the two dots on the upper index, right here on the upper. That means that you're finding the second derivative of the position versus time. That has to be equal to a, and that's when I'm trying to say that you need to have the acceleration, yes, and the acceleration is a function of time. With initial conditions, you had to have initial conditions, yes, at time zero. I mean, at the initial time, you have an initial position for your system, and then you also have to have the velocity. You have an approximate numerical solution. Okay, so this is for xn. So xn is referring for a later time. Okay, and then this is right here other times tn. So I mean for time 1, 2, 3, 4, 5, 6. So you can continue moving on time. It has to be equal to initial time plus n, because it's step number 1, step number 2, step number 3, step number 4. So n is gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and go forward. And then we have this delta t. This delta t is defined as a time step. Okay, so how far you want to have your calculation. So if you put, for example, that the time step is equal to let's say 0.5, yes, and you begin at 0, then you will find a 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and so on and so forth. Okay, and then how we can find the position. You can find the position now, that will be x1, because the new position is equal to the initial position plus the velocity, your initial velocity, and you had to multiply the initial velocity times the time step plus half the acceleration. Then you have that to multiply times the time step to the power 2, or also the time step to the square. Okay, and then later on, if you want to find it for n equals 1, 2, 3, 4, 5, 6, 7, and so forward, you only have to do the interaction, and this repeats and this continues doing again and again. So once you have your initial positions and your initial velocity and your acceleration, you can calculate for x equals 1. That's going to be the new position, yes. And then having this new position that's called x1, then you can calculate for x2. And then when you have the new position on x2, you can calculate for x3, and this goes and continues forward. Okay, this is straightforward, and it's actually the way that we do molecular dynamics. Okay, and probably for people who doesn't remember, and probably that has to be more into the college level, but this actually differential equation that is right here, where you have the x and the 2 points, the 2 dots on the upper, and that equals to the acceleration time that has to be as function of the position and time. That's exactly why it's Newton equation. Okay. Usually when you're in high school, you see Newton equation as a force equals mass times acceleration. Okay. But it's pretty much the same. So this is basically all that we need to do molecular dynamics. Now, if we continue, so what we have to do, we have to predict the evolution, and that will be the position, x, and the velocity, or also the position and p is the same thing as the momentum. I mean, how you find the momentum, you only had to multiply the velocity times the mass. Okay, so usually we're working with velocities. Okay, but if you want to find the momentum, you only had to multiply the velocity times the mass. Okay, and then you had to use your Verlet numerical integration, the one that was referred in the previous slide. And then the first thing that we had to do is number one, you had to have the initial position, you had to have the initial velocity, you need to have acceleration, okay? And with that, you can do molecular dynamics, okay? I'm gonna introduce these problems, yes, before going into more complex system. And there are two classical problems that are going to help you a lot to learn more about how we do molecular dynamics. So that will be number one, and it's going to be the three-body problem. I'm going to explain this for people who have no idea what's the three-body problem. And then the second one, and probably this is one of the common ones that students see at high school, that's called the projectile motion. Okay, so how in these three problems, these two problems, we can actually do molecular dynamics. So I'm gonna go into the first one, and that has to be a projectile motion. Okay, this is something that students at high school level see constantly when they're taking a physics class, and pretty much is you have an object that is under the influence of the gravity. The gravity is going down. Okay, and then you have an initial velocity, okay, and based on that you let the system run, and then you can predict the trajectory that usually is going to be a parabolic. So you can see right here I have my initial position. Usually this is 0,0, and then I have the gravity is acting on the object, and then I let it run, and then I'm gonna see how this moves. They're gonna go into a maximum height, and then probably it's gonna go down. How we find the solution to this problem? Well, I have to go back to my Verlet, okay, numerical integration. So I'm gonna go and I'm gonna show you guys how to find a solution to the projectile. Oh, probably I went to YouTube. I don't want to go into YouTube. I'm gonna explain to you how to find a solution to the projectile motion. So I going to, oh my goodness, what I'm doing right here, you can see everything is on my computer. So so let's try to find the solution to the projectile motion using the Verlet integration. So pretty much we have to have the initial positions. Oh, I'm again going to YouTube. I don't want to look at my YouTube channel. So probably you want to look at my YouTube channel actually. Okay, so you have to have the initial position of the system. Okay, in this case is x equals 0 and y equals 0, and then you have to have the initial velocity, because right now if I go back to the presentation, because we are caring about 2 dimensions, we only have the x and the y. So right here we find that for the x component it is going to be 2, the y component is going to be 100, then the mass, that is m1, I put 10, but if you want to make it easy, you don't have to put it down, because if you can see when we go into the integration, we don't have the mass. We don't need the mass. At least here we don't need the mass, okay? If we want to find the momentum, the p, we need the mass, okay? But pretty much if I had a velocity, I only had to multiply times the mass and I can find the momentum. And then I need to have the acceleration. Well, right here I put 0 and 0, but that is not, I put ax equal to 0 and ay equal to 0 because that's gonna be like to initiate my acceleration. And if I go into my main program, I have to have my time initial, that's usually 0, and I want to run a simulation for 25, probably it's going to be 25 seconds, and then I had to define my time step that is going to be equal to 0.10, okay, and I want to go here. This is really important, right? Because when I have acceleration, I put right here that for the x component we have 0, but for the y component we have 9.8, okay? And 9.8 is actually the constant for gravity, and that's exactly what we have here in the drawing. You can see it. I don't know. Oh, you are able to see it because you don't have the. Let me go because I'm blocking with my webcam. So you can see it right here now. You can see it. So right here we have the gravity is acting down. Okay, so that has to be negative 9.8. Okay, and then in x we don't have any acceleration. Okay, then we're gonna use that Verlet integration. So if you can see, this is exactly when I define when we have the Verlet integration. So here we have x. This is my initial position, and actually it's exactly what we have on my equation right here. If you can go back, you can see that I have x initial. The reason why I have this plus equal, and then we have the velocity times the time step, that's dt, and then plus half the acceleration, and then the times 10 to the square, I put like dt times dt, okay? And then also we can find the velocity, okay? Once we have that, okay, then we can do, because that's gonna be the predictor, and we have to have the corrector. But anyways, while we have that, we can find the position x1. Now when we have the position x1, we can find for the position x2, x3, x4, x5, and so on and so forth until we end, okay, in 25 seconds. So I'm gonna run this program, okay. I'm gonna run it for you guys. I'm gonna have only to compile the program, and then I'm gonna run this, okay. You can see that I have the time, the position in x, and the y, okay. Now what we have to do, because I actually want to have a graph, there are many ways to do a graph. I'm gonna go right now. I'm gonna copy this, okay. I'm gonna copy, I'm gonna paste probably, and then I have my time, my x, and my y. So I'm gonna grab the x and the y just to grab the trajectory, because that's something that probably we want to see. And I can go here, probably want to have a score plot x and y, and this is, so this is what I have obtained. So this is my graph of the trajectory, okay. And probably, if you remember, this is gonna be parabolic, okay. As you can see clearly, okay, we have the x and we have the y. So I can pretty much say that at the maximum height is gonna be around 500, yes, and they're gonna be around 20.6 seconds. Then when it goes down again, it's gonna be at the distance of 40 horizontally. And just to make sure that I'm right on my calculation, I'm gonna grab the time and the height. I'm gonna grab the time. I'm gonna grab the y. Okay, just to see how the graphic is, because it's a trajectory. Okay, of the object. But I'm gonna try to grab the time, and I'm gonna grab the y component, and again I'm gonna try to plot this for you guys, where I can go to do the score plot. Okay, I'm gonna put it right here. So this is the height versus the time. Okay, now guys, for you to get an idea, I'm gonna do a trend line. So I'm gonna grab this, I'm gonna do that. I'm gonna try to find a trend line for this. It's gonna be polynomial, it's gonna be second degree, because probably you remember from high school when you have a parabolic trajectory, usually you have to use a quadratic equation. And then I'm gonna have, for me to apply the equation right here, I'm going to make this, because I don't like it, it's too small, probably can increase the font a little bit. And I want you to see, people, this is really important for you, because this is the height as function of time. We can see that when we look at the equation, the y, here x squared actually represents the time, okay? And probably for some people it's gonna be really familiar when we have a negative 4.9. Yes, probably if you remember, this constant right here is actually the gravity divided by 2. It's half the gravity. So if the gravity is 9.8, then half the gravity, it will be 4.9. So the reason why we have here 4.9. This is not a coincidence. And actually we can go into the equations of motion. Probably to you, for if you remember, just to give you an idea, so we can compare what we have right now with your drawing. Oh my god. Right here so we can see it. But I want to have the equation. I want to have the equation, and put it right here so we can see it. Okay, here it is. Okay, so pretty much exactly what we have right now. So as you can see, this right here, this thing is as a t squared, exactly what we have right here in the drawing. Exactly the same thing, you know. So this is the velocity actually, and we already, and if you remember this 100, it was right here. Okay, then we have, this is like 0 because it's pretty much like 0. Because remember that was our initial condition, to be on 0, 0. So this is how we predict, okay, using a numerical integration, how it's going to be the behavior of the system. And actually we can look how it's going to be the trajectory, okay. And what I needed to do the calculation was pretty much as defined here. We need the initial position, the initial velocity, and acceleration. And once we had that, we can predict for n times. Now we're gonna go into another example, and that's gonna be that will be the three-body problem. Okay. This is a classical example that we have, and pretty much we were solving this solution. We have 3 objects, okay, and then we have to have how they're gonna move over time, okay. Typically the solution to this problem is gonna be numerically, because it really had to find an analytical solution to the problem, and we have to have an acceleration, okay. If I go back, I told you that we have to have acceleration, we have to have initial velocity, and we have to have the initial position. Typically when we are dealing with three-body problem, we go into the gravitational potential. I'm probably going to classical mechanics, or if you go into high school, you're going to remember that the gravitational force is equal to force equals the mass, capital M, times the small mass, and then you have to divide that by the square of the distance. Okay, and typically when we're having these solutions, we don't actually have the force. We want to have the potential. Actually, right here, the potential U. We have to have this potential. So pretty much when we have three objects, it's therefore you have, this is a universal constant G. I mean, usually you can make it equal to 1. You don't have to be very precise. Then we have mass 1, mass 2, divided by the distance between the first mass and the second mass, and then we have the m1 and the m3, and then that divided by the distance between 1 and 3 plus m2 and m3 divided by the distance between the second and the third mass. And this is my gravitational potential. Okay, and you're gonna ask me, okay, why we need the potential, why we need that? I mean, if you remember when I was playing this equation right here, we need the velocity, we need the initial position, but we need acceleration. Why I'm asking for the potential if I need the acceleration of the system? And the reason is because if you remember your classical mechanics, okay, from the potential, okay, you can find the force, okay, and if you have a force, you can find acceleration, because remember the force is equal to the mass times acceleration, according to Newtonian mechanics. So if I had a force, I only had to divide the force by the mass, and then I can find the acceleration. Okay, so how we find from the potential, we find the force? Pretty much, if we have our potential U, okay, and you calculate the gradient of the potential, you obtain this right here. This right here is actually the gravitational force, okay, and when you have the force, you can actually find the acceleration. And I'm gonna go right here into this right here, because I put this right here for everybody, and I'm gonna put here in the center. I'm gonna increase this a lot. This is the acceleration. I'm gonna highlight this here. This is the acceleration for when we are dealing with gravity. Okay. Now you're gonna say, wait a minute, this is a little bit different to the equation I had before. Well, not exactly. If I have here, because I don't have right here, this is the solution, but if I multiply, times capital M, yes, then that's gonna be equal to the force. Okay, and I have to put here a capital M, okay, and this right here, this equation right here, exactly the one that we got from this, from having the potential by having to calculate the gradient. We found this equation right here. So this component right here is actually the acceleration. Now there's another thing that we have to consider right here. Probably gonna ask me, hey, wait a minute, if I go back, I'm gonna go back to this image. Okay, hey, wait a minute, I have here the R3, but I don't have here this epsilon. I never had this epsilon right here. Well, why is this epsilon? Why put this epsilon right here? Why I had to put it? We had to consider the following. When we're doing molecular dynamics, we are trying to do a numerical integration, okay? And I'm gonna increase the size of this image, okay? This is a potential energy graph, okay? Probably this is gonna be for gravity. So look at it. This is going down and down and down and down, and the distance goes far away. But this continues and continues and continues forever. Okay, and that will be because gravity is a long force, so it can act a long distance. You know, probably you remember that from your high school classes. But if we are trying to do a numerical simulation, this is not gonna continue forever. You have to actually cut this. And that's actually what people do when they're doing the simulation, because the interaction cannot last forever. So you have to give it like an R cut, okay? And after that, everything becomes zero. There's no more interaction. That's the problem number one that you have when you're dealing with this kind of simulation. What's gonna be your range of interaction, or how long is gonna be the range for the interaction? And after that, you cut it, and everything else is gonna be zero. Depending on the R cut that you use, okay, the simulation is gonna change a lot. Okay, now also here, okay, I added this epsilon, and probably for some people who understand why I added this epsilon, that's a constant, is because we don't want the objects to be too much close together, because if you remember, this R, or this distance, cannot be zero. Okay, because if it becomes zero, if the distance between the two objects becomes zero, then this is gonna blow out. Okay, there's gonna be a lot of numerical issues and numerical errors. So that's the reason why we had to add like an epsilon to say, okay, wait a minute, this can be closer and closer and closer. There's gonna be a moment like, wait, you're not able to go any further. You have to stop right here because you are not able to continue. Because if you continue, then this R is gonna become zero, and then numerically is gonna become an infinity. There's gonna be an inconsistency. So that's the reason why we had this epsilon. And you have to be very careful, because actually the epsilon that you are adding also affects your simulation. Yes, it's not the same to have an epsilon of 1 that having an epsilon of 0.01. Okay, and yeah, but doing this problem, okay, we are learning a lot about how to do molecular dynamics. I'm gonna show you, okay, I'm gonna show you how to do this problem right now. I'm gonna go and exit from here, and I'm gonna close this already. Then I'm gonna show you the three-body problem right here. I'm gonna compile this for you guys, and also actually gonna what happened right here? Oh, okay, let me open my main CPP so I can see. Well, this program actually right here, because we have a copyright. This is from 2002, and I may have some modification to the program. And actually here we can have that information. But pretty much what I'm trying to explain to you guys is how we do the calculation. So we had to have the initial positions, we had to have the initial velocities, and the mass. What about the mass? You don't need a mass, because as you already saw here, I never told you about the mass. But if you want to make it simple and you don't want to go into issue, you can make the mass equals 1. And there you go. Make mass equals 1. Try to reduce the units also. I mean, try to make this g right here, this universal constant, equal to 1. And you don't have actually to give it the exact number, the exact number of that constant. You can make it equal to 1, and you can use reduce units. And anyways, I want to explain this because this is a lot of things that we have to go into, but I really want to explain to you how we do it with a Verlet. So right here, this is crazy, right? Let me go here so that we can go and see. Where wait. I want to show it to you guys, but I don't see it right here. I want to see it. Oh my god, I'm lost. and I have used this. Okay, here we go. This is the Verlet integration. Okay, and probably you remember this is the equation that I was referring before. This is other equations that we are actually that we are using right here. Yes, copy and paste in the equations, and then I want you to explain to you what's going to be the acceleration. So how we find the acceleration? Probably can go here and put ax. Where am I? Okay, let's see what I have right here. Okay, here we have the acceleration. Okay, this is exactly, okay, this acceleration is exactly what we got in this equation right here. Okay, is ij, so it's a12, a13, and a23. Okay, so the reason why we have here the difference between xi, xj, xij, and then here we have epsilon to the square actually right here. So this is our acceleration. Remember, if we have the acceleration, we have the force. Okay, and actually some people say, we need to find the force of interaction. Well, if you want to find the force, you only have to multiply the acceleration times the mass, and then you have the force. Okay, but for our consistency, we don't need the force, we only need acceleration. Okay, but if you want to find the force of interaction, you only have to multiply times the mass. Because remember, the force equals m times a. And based on that, we can run our program. Actually, I'm gonna do it right now so you can see an example how pretty it's gonna be. And some people really like this kind of problems. Well, but I have to compile it to compile this. And I have it right here because sometimes I forget how to do it. Then forget the warnings. I don't care about the warnings. I know it's working. So there we go. I'm gonna do it. Okay, so here we go. This is pretty. You can see how this moves. And I don't know, can you see the trajectory? Can you actually see? Probably I have to change this. I don't know if you can see the three bodies moving around. Okay, and this is pretty much how we calculate the position. Okay, how we calculate the trajectory up. Actually, we can see how they move. Actually, I don't know. Can you see it? Because this is really probably had to change the background and probably increase the size of the red balls. That will really help you to see it because I can see it clearly, but I don't know if you guys probably can. If I get a little, there you go. Now I can see it clearly. So you can see how they move. Okay, and we can run this for different conditions. Okay, we can put the particles in different places and we can give it different velocities to see what happens. We can change the epsilon value. Okay, so we can play around with this a lot. Probably gonna give another example because some people really like to see this. Let me go here and I'm gonna go here. I'm gonna give you another example. I mean, this is gonna be a lot of things that happens. So you guys need to see. Oh my goodness, this is crazy. Let me see. No. Wait a minute. This is not good. Okay. Wait a minute. Let me close this right here. Okay, we had different scenarios. So I'm gonna try another one just to see what happens if we change the positions, how we change the velocities, and then we change the masses. The masses, yeah, I mean, remember that in the acceleration we have the small m. I mean, I don't know if you see it because you're blocking, but you can see right here that when we have acceleration we have this small m. Okay, but the force you had to multiply this times capital M. So if I want to find the force, I mean you have to multiply this times m. then here I had to put another m, and that will give me the force, you know. So in case that you're not understanding this, that's gonna be the force. So I'm gonna make another scenario for you guys. I need to see how this runs. I'm gonna save this. I'm gonna run again. It's gonna be a little bit different. And then I'm gonna increase the size of this. There we go. And can you see it? There we go. How this one? Can you see how it changed? There we go. There I can see it perfectly. You can see how they move. Now different. So one is in the middle, right? One is in the center. Okay. One in the center have mass of 10. Okay. The ones on the outside have a small mass like 1. Yes. So that is what happens. It's supreme, and I really like it just to see how they move out. And everything that you see right here is done by numerical integration of the Newton equations. Okay. So you can play with this around a lot. Okay. And then to go into the next presentation, next slide. What is molecular dynamics in summary? Okay, and this is the summary. Number 1, we can predict the evolution of n objects as function of time using Newtonian mechanics. Okay, and number 2, you have to remember to use a numerical integrator. The numerical integrator that we are using right now is, and actually right here in the presentation. Okay. And then you have to know the initial positions, velocities, and acceleration of system of particles. Number 4, and it's important, how we obtain the acceleration. So pretty much you have to have acceleration, you have to obtain your potential. Okay, from the potential you're gonna use the gradient, and from the gradient you're gonna find the force. So the force equals the mass times acceleration. So acceleration equals the force divided times the mass. Okay, that's acceleration. And then we have acceleration, we have the initial position, and when we have the velocities, I can run this. Okay, and finally, you had to repeat the process. So once I have my new velocities and my new positions, then I redo it again, and I redo it again, and I redo it again, and I continue, and with that I can find gonna be the next trajectory. I'm gonna stop right here because and actually I'm right here right now. I'm right here. I'm actually right here on the number 1, what is molecular dynamics. I haven't finished with what is molecular dynamics. I'm gonna continue with this, but I don't want to make this video too long. Okay, and then after that, because I was actually planning to do this in one presentation, but I think I'm gonna need like 5 or 6 to continue this. But right now we are in what is molecular dynamics. I'm gonna give you the topic is gonna continue. So right now we did it for 3 bodies, okay? And you're gonna ask me what's gonna happen when I have n bodies. It's gonna be the same, or what's gonna be the problem? What's gonna be the issue? Well, remember when we are working with a lot of when we're working with a gas, okay, when we're working with a gas, or we are working with a real system, probably I'm gonna say helium. Let's say that we're working with helium. There's a gas. You have a lot of objects, man. You're talking about the Avogadro number, okay? So and that's gonna be what I'm gonna go next when I go into the topic, because how we do it? How are we gonna find things when we have large numbers? And the answer to that is going to be that pretty much we have to go into what is called statistical mechanics, because if you remember, when we are working with large quantities or large number of particles, we use statistics, okay? And so I had to go and review what is statistics, okay, and how this applies to physics, because probably you remember from statistics we can find properties like pressure, temperature, and so on and so forth. All that can be obtained from the velocities, or it can be obtained from the collisions. Okay, so that's gonna be next for my next presentation. Okay, but because I'm still here into what is molecular dynamics, and probably please, people, give me comments and tell me how I can improve this. If I forgot something, if you want me to give you my presentation, I can give you a presentation. If you want me to give you this script so you can run it, I can give it to you. If you have different questions, just let me know. I will try to answer. And thank you for everything.